Good morning. My name is Shanil Chandra and I will be walking you through a very short video on the need to study water if you're a paramedic. So the questions that we are going to be addressing in this short video are really what are the aspects of water that are particularly relevant to a paramedic. Because you are going to be looking at quite a bit of chemistry here, we are going to be basing our science on an excellent science resource or chemistry resource titled Chemistry, the Molecular Nature of Matter and Change by Martin Silberberg. Any edition, 6th edition upwards is always a valuable resource from this author. So before we begin by looking at the structure of water and its behavior, which really is what is the driving force for water being so important to paramedics, is we need to look at why we are studying chemistry when you are looking at when you are studying paramedic science. Well, if you're a person of science, you really know what is happening around you. But when you study chemistry, it is able to tell you, particularly as it goes at atomic levels, why something is happening the way it is. So really, from what is happening through chemistry, you're able to explain why it is happening. And that is the most important thing discussed in this video. Well, water is a compound. That means it's made of at least two different types of elements. And these elements are oxygen and hydrogen. The oxygen-hydrogen bond is of this nature. There's a central oxygen bonded to each hydrogens. And oxygen is a very strongly electronegative element. When we say electronegative, we mean in any bond that oxygen forms, it tends to pull electrons towards it, particularly when it is combined to hydrogen, which has lower electronegativity compared to that of oxygen. So as a result of the oxygen pulling electrons in the bond towards itself, it acquires a partial negative charge in the water molecule, whereas hydrogen acquires a partial positive charge. So what you end up with is the water molecule having distinct negative and positive centers or poles, which is why we say the oxygen-hydrogen bond is polar, or water is a polar molecule. Because of the polarity of water molecules, it presents possibilities for strong intermolecular attraction forces. Remember, there are negative ends and there are positive ends in water, which means between oppositely charged ends of water molecules, you will find attraction forces building up, which we call intermolecular attraction forces. Likewise, when you dissolve charged species or charged particles like ions in solution or in water, similar attractions build up between the ions as well as the water molecules. And that leads to what we call solvation or dissolution, really. What we will see that through an example. Here we have an ionic lattice or an ionic compound comprised of anions bonded to cations. The green represents the anion, the blue represents the cation. At the beginning, the salt is made of these ions constituted together as an electrolyte compound and obviously solid, which you can see when you weigh it out or when you measure it out. When you add it to water, which is depicted here by these molecules, red and two greens, following this convention here, you find that slowly the ions start to break apart. So they start to spread away from the ionic lattice and start becoming outward into the water. When that happens, the anion is surrounded by the positive ends of other water molecules, which obviously are denoted by green and constitute or represent hydrogen. And likewise, the cation that was formerly attached to this is surrounded by negative ends of the water molecules around it, or oxygen atoms. Because of that, eventually the entire ionic lattice breaks up, and you end up with all the cations being surrounded by oxygen ends of water molecules, and all the anions being surrounded by hydrogen ends of other water molecules, deliberately keeping the ions apart. When it does so, it ensures that the ions do not reform or reconstitute. which is why when we weigh out or measure out a salt, we find that the salt, when it goes in the water and is mixed, does not reappear. What is the application of this electrolyte dissolution or solvation in the daily life of a paramedic? Well, here is where you will find a solution and dissolution on a daily basis, that through a saline solution. Now, a saline is administered through intravenous means, which is really a solution of electrolytes, to address electrolyte shortage in the body, which could arise due to severe dehydration, or it could arise due to unexpected sudden events such as onset of fever. In that case, the body needs to replenish its electrolytes, and you need to supply that intravenously through the saline drip system. Now, saline doesn't only contain one type of salt, it contains many salts, and in preparation of saline, water's great solvation powers come into play every time. In fact, saline that is used commonly in paramedic terms is really, in chemistry terms, a solution of any particular salt. So we look at the second function of water, which is that of a temperature regulator. And before we do that, we look at a concept called the specific heat capacity, denoted by a small italicized C. And the specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. So really, it's a measure of how much heat needs to be supplied to a substance so that its temperature rises for 1 gram by 1 Kelvin. And the specific heat capacity is really what we use to measure how much heat can a substance absorb before its temperature starts to increase, or how much heat does it have to release before its temperature starts to drop. And when we do that, we look at some common examples or common materials that are presented here. You're quite familiar particularly with these solid materials: wood, steel. Obviously, steel doesn't absorb much heat, it transfers it, which is why you can't poke a fire with steel, because it'll get very hot. Now, if you look at the list here, you'll find that water is highlighted, particularly because of its extremely high specific heat capacity. It's the highest on the list, and it actually is even higher than that for wood. Now, nobody ever realizes this, that wood actually is going to turn hotter faster than water will. So that tells you how much the capacity of water is to absorb heat. Why is that so? It's due to the hydrogen bonding in water. Remember, we looked at very strong intermolecular forces of attraction between water molecules. The strong intermolecular forces in water are called hydrogen bonds. These hydrogen bonds can absorb a lot of heat before they actually break up, which means it takes a lot of heat to be delivered to water before it changes its form into gas. And that allows water to absorb quite a lot of heat without disrupting its form or behavior. How is that relevant to a paramedic? You may be encountering situations where there has been in an area of high heat called a burn, where you may need to alleviate the condition by removing the heat away deliberately from the affected region. And in that case, you are going to be looking, most likely than not, water, because water is commonly used as a coolant. And in almost all burn cases, the advice immediately given is to let it cool down by putting it under running water, if possible, or just immersing the affected region in cool water. Not cold, but cool water. That advice actually exploits the high heat capacity of water to actually absorb the heat away from the region without disrupting its own functioning or making the injury worse. So in summary, what we've done is we have examined the structure of the water molecule, which allows its unique attributes and aspects which are relevant to you in your daily life as a paramedic. The polarity of water allows for its wide range of solvent uses, or its applicability to dissolve a wide range of electrolytes. And the strong intermolecular forces allow for greater heat capacity, which allows heat to be conducted away from burn areas, therefore allowing the areas to cool. Thank you.